Everybody see that? Yeah? Is that file? Yes. Okay. So, anyone play Tetris? Okay, I'll start my prayers. Okay, so I was really bored. I think I was procrastinating at work one day, and I was reading all these blogs, and I came across this blog by Alexander Dickinson over there about how he wrote an emulator and how emulators are awesome, and it inspired me to write my own emulator because there's all these challenges you have to, I guess, face and solve, and I thought it'd be really educational. So I wrote my emulator, and it sort of works. And I thought I'd tell you about my experiences. So that's me. I'm Radad Sleeman or Ray Sleeman. Pretty regular here now, so you might know. Not there my details. Yeah. Cool. All right. So I wrote a Chip 8 emulator in Node.js with CoffeeScript. Some people say, why would you want to write an emulator? Well, it's just heaps of fun. That's like the most thing. That's like the primary thing when you do your own projects. You want to have fun, but you also get to face a lot of challenges, and I think you may become a better programmer because of it, or it may not do anything. But yeah, I thought of all these challenges. So that's why I wrote it. I used the language CoffeeScript because I'm a big fan. If anyone isn't a fan of CoffeeScript, I'm not a fan of you guys. A lot of people hate it, but I think it was amazing. So, hopefully, people can see how clean and concise the language is. But yeah, so that's basically why. And what's in it for you guys? What are we going to cover? Well, first you got to learn about emulators in general. If you guys don't know what they are, spend half your childhood playing them, like me. You can afford games. We're going to walk through the implementation. So for people who haven't done bitwise operations much, it'll be pretty cool showing you how they work and some of the cool things you can do. Plus, if you guys saw earlier, I took a different route to rendering, and that's actually running in a terminal. So I'll teach you guys how to, I'm not sure if it's the best way, but yeah, I'll teach you guys how to, don't press that. I will teach you guys how to communicate with the terminal with Node.js, or pretty much any language where you can print out to the console. So yeah, it's heaps of fun. We'll be processing opcodes and reading assembly and stuff, so we'll feel like we're computers at the end of the day. Okay, so we're going to start with what are emulators, or emulators in general. So basically, over this side, you can see all these really old school devices. That's a Nintendo Entertainment System, and that's the Apple Amiga 2 on it. Not Amiga, sorry, Apple Lisa 2. And the reason why you want to, basically an emulator is something that runs old school software, or emulates a system to run old school software, or it doesn't even have to be old school, just on a different system. And some of the reasons why you want to do that is you want to relive old classics. Like you can't get your hands on a NES or Nintendo Entertainment System. You want to play Mario. You want to relive your childhood. You can do that with an emulator. You don't have to go and hunt at cache converters and pay a ridiculous amount, something that might not work. Or you can run really old software. So there are some practical applications as well. But I guess, yeah, the whole idea is just to have fun. Most emulators are used for games. This is basically it. When you write an emulator, the primary thing you emulate is its processor. But then you have to emulate every other piece of hardware that is used by the applications for the application to work properly. So that's basically what emulators are. Okay, so first of all, what is Chip 8? So I told you guys I implemented this Chip 8 emulator. We saw earlier I was playing Tetris with it. Chip 8 is a type of processor that never really existed. It's actually a virtual machine. It was designed to be emulated. And it's a really good first project to get your hands dirty with emulation, and it will teach you a lot, and you'll get pretty knee deep in emulation, and it will set you up really well to taking on more challenging projects like emulating the Nintendo Entertainment System, or maybe the Game Boy, or who knows, if you game, maybe an Xbox 360. But today we're going to look at the chip 8, and pretty much all processors have these things, and we're going to talk a bit more about each of them. So I guess you have the best way to look at a processor is just one big loop that keeps looping around, and that's the loop over there. It's the fetch, decode, execute loop. So you fetch something from memory, an instruction from memory, you decode it, so you figure out exactly what that instruction is or what has to be done, and then you do it. And then you move to the next position in memory, and you keep doing that. And that's basically what the processor in this computer is doing right now, and things like that. But there's a bit more. It gets a bit more complex. You don't just have a loop in memory. Opcodes are what we call the instructions you grab from memory. The stack, anyone that writes any programs will know what a stack is. Works exactly the same way, but on a lower level. Now, processors are really, really dumb. They don't even know how to multiply. There's no multiplication instruction, or maybe there is, but not on the chip 8 or the processors I've seen. So they use registers as, I guess, places to do working out. So if you were going to do a multiplication, I guess, operation, you would use 3 registers, and you would increment things and add the registers together, and then 50 instructions later, you've multiplied 5 by 5. So that's what registers are used for. You've got timers, so the CPU can keep track of time, or can cause delays, and it doesn't just keep processing at an uncontrollable rate. Interrupts. Now the chip 8 doesn't have interrupts. Maybe it does, but you don't have to implement interrupts. But basically, that's how you communicate with the processor, or the other pieces of hardware can communicate with the processor. So when I press a key on my keyboard, with that key, but basically my processor is executing things from memory, and it's running, and an interrupt will come in and just step in and stop execution, and then run another routine based on whatever I pressed, and then that may affect how the program runs overall, and that's what an interrupt does. And finally, processors have to interface with hardware. So, if you want to talk to your sound card or your graphics card and things like that, the way processors talk to hardware, and if you were emulating, you'd have to emulate that communication as well, there's a number of ways, but I guess the most commonly used way is via memory mapped I/O. So there's a certain address range in memory where you will write to, and then the other device on the other end will read that part of the memory, and then that's how the communication works. And that's basically it. That's what a processor has. It gets really complex when you look at more modern processors. The chip 8 is really simple, and that's why we're going to be going through it today. Okay, no, sorry, not that. All right, so let's look at some code. Alright, so this is my processor. It's written in CoffeeScript, and there's 287 lines, but there's a lot of comments, so it's probably only 220. And these are the components, just so you guys can see. I basically declare all the parts of the processor here. And sweet. So yeah, I've commented it, so if you guys look at it, this will be hosted on GitHub, so if you just want to see what everything does. Yeah, I basically declare every part, which we'll walk through in a moment. And I have to implement each of the opcodes, so the opcodes are the instructions that the processor acts out on. This is the CPU loop, the fetch, a decode, execute loop that we were talking about before. This is basically the loop here. And actually, it's the whole thing here. And then I have another loop that does the drawing cycles as well. So that's basically the whole emulator. And yeah, what we'll do is we'll start with its components. So before I start, everything is pretty much denoted in hexadecimal. And the reason why we do that is it's just a lot easier to read, especially when we do things like bitwise operations and we do things like bit masking and stuff like that. It's a lot easier to see what's going on, and I'll show you that when we get to actually processing some of these instructions. If it's actually put in hexadecimal. So as you can see here, if anyone's not familiar with, actually we'll get that. So we have the first thing we declare is a reference to opcodes. So basically this is an instruction that's going to be processed or is being processed at the time. The chip 8 has 16 registers, or 15 registers and general purpose registers and one special register, where it does all its working out and it stores pieces of information while it's computing an operation. And as you can see here, this is basically what this is. If people aren't familiar with CoffeeScript, it's just a one-line for loop where I iterate over a range, which is 0 to 15, and then I assign that value to. You'll see me doing this a lot. So I'm assigning for basically 0 to 15 will equal 0. It's just me initializing the array. We'll get to these in a moment, or when we look at decoding opcodes, they're kind of special. This is another register. It's just a special register that's used in, I guess, arithmetic operations. F is basically, it's just static. It's always going to equal the number 15, which is our special register, which is used as a flag. So when when operations, mathematical operations overflow or we exceed the amount of space that number can hold, we will set this flag to 1 so the program can react to it. And there's other uses of F of the F register as well. Okay, so like I was saying before, a processor fetches instructions from memory, and its current position in memory that it's looking at, or the next instruction that it's going to be fetching, is what we refer to as at the program is what we refer to as the program counter. So if you have a look here, the program counter is set to read at the 512th memory instruction, which basically means that's where the ROM starts. So if you read the chip 8 specification, it will say that programs are loaded at this part of memory, and we want our process to start executing at that point. A stack, well, I've implemented the concept of a stack with just a normal array, and the pointer, or really it's called the stack pointer, is basically the position in the stack that you're on. It's always going to be the last element in the array, but it was a lot simpler for me to implement it with as an actual variable rather than figuring out the length of the array and being at the end. The chip 8 has 2 timers. One's a sound timer and one's a delay timer, and that's basically how chip 8 plays sound. So I guess there's a count every time the CPU cycles, or it's supposed to count down these timers at the rate of 60 Hertz. But if the timer isn't 0 for the sound timer, it will just beep. It'll beep your terminal, or it'll supposed to play sound. And that's basically the sound capabilities of this system. And the delay timer, which is basically it's used to stop execution for a certain amount of time, and I guess pause and things like that. So I guess you'll see how that's used in the program as well. These aren't part of the chip 8 specification, but I just use them to handle things in my emulator. I use a buffering. I guess the way I draw to screen is via a buffer. So the screen is just basically a multi-dimensional array of XY values for coordinates or pixels, and I need to have 2 of them to set up my buffer, which we'll look at in a second. And for debugging purposes, I sometimes print out the output of my emulator, the actual opcodes that are being processed, instead of drawing the image to the screen, and that's basically what that flag is for. And this is sometimes the processor needs to pause, so I have this to start or stop the processor. And yeah, this key down is basically what key I press last, and key press is the function that executes. Or basically, there's two ways to handle key presses or key presses have to be handled in 2 different ways in chip 8, or in the way I've architected this emulator. So this is actually going to be a function that will have 2 different implementations depending on the time that it gets called. So that's basically all the parts of my processor. Now, with chip 8, it has some predefined graphics that are hard coded into the ROM, and that's probably to make development of chip 8 games much easier. And so I've had to include them as well. Now, this will give you an idea about how graphics work or how graphics are programmed in the chip 8. They're basically sprites, and each byte represents a line. So if we have a look here, hopefully this is readable. Let's see that. We're looking at the letter A. So if we go to line 44, that's basically a sprite representation of the letter A. And if you look at 0xF0, which is basically, this is its binary representation. And if you have a look at the way the binary is, you can actually see that we're drawing an A with binary. And that's actually rendered to screen the exact same way. So yeah, so it's the tricks that people had to do back in the days when, they only had 1 megahertz of processing power. Things we'll never have to worry about. Okay, so this is my ROM loader. I do it all in a couple lines. So I basically grab an argument that I pass in when I run my command from terminal, and that argument should point to a ROM, and I just get the JSON output of that, which is an array of bytes. So I grab that, and then I just store that for a second. My memory is just an array. Could have used like an array buffer and things like that, but wasn't game. And yeah, so I have to preload my memory. First thing that gets loaded in the specifications is fonts. So this is always at the start of memory, the font information. And then I load my ROM, which you can see here. I'm just looping through this ROM array, and I'm loading it at position 512 and onwards, which is where my program counter is pointed. Okay, so I map keys. The keys is on my keyboard, map to the values as per the chip 8 specification. And you'll find that when you implement an emulator, that's basically what you're doing. You're reading a piece of specification, and you're implementing it the way it says word for word, or the program won't work. Okay, these are all my opcodes, so basically the instructions. We won't go through them until later. But yeah, there's 35 opcodes or operations that you can do in a chip 8, and you have to implement every single one of them, hopefully as accurately as possible. And we get to the CPU loop, which is the heart of everything, and where things get more interesting. Okay, so what we're going to do is, actually before I go, instructions are actually 2 bytes in size. So what we're going to do now is we're going to process an instruction as if we were the computer, and to show you how this fetch, decode, evaluate loop works. So first thing we do is we get our program counter, which is our position in memory, and we grab whatever data is there. So let's say we were playing Tetris as we were before. We would basically grab this, which is A2. Let's see what that is in hexadecimal. That's just the number 162. But don't worry too much about that. That's just if you wanted to know what that was as a number. But we grab A2, and then we do a little trick. Because each instruction is 2 bytes long, so we join them together. We join them together. So what we do is we do a bitwise shift left, which is what that does. I've seen that. 8 positions to the left. So let's say, what was it? Was it 6? It was A2. So let's say we had A2. We move it to the left 8 positions. So we end up with, let's say we were, now in hexadecimal, and remember I said it's much easier to see things in hexadecimal than binary and the normal decimal values, and this will be apparent now. So we move this 8 positions to the left in binary, but in hex it actually only moves 2 positions. So We end up like that. And then we do what we call an OR operation on the second piece of memory, which let's just go in here and see what that is. B4, which basically joins these two things together, or adds them together. So if we were to add, I don't even know what number that would be now, but don't worry. Basically what it will do is it will mean we can add B4 onto the end. And that's basically how we got the instruction A2B4. Okay, remember how I said I'd explain what X and Y were a bit later, so it would make a bit more sense. But X just refers to the second position in our instruction, and Y will always refer to the third position in our instruction. And we do some crazy bit masking over here, and we shift things around to extract that position. Now, the reason why we do that is that these have a definite value, or they're used a lot when we actually use instructions. So if you can see, I use the X variable and the Y variable a lot. So grabbing them at this point is really efficient and really easy. So that's why we do this, and that's basically our fetch part of the processor. Now, the next part is our decoding. So how do we figure out exactly what instruction this is? What is A2B4? What are we actually doing? Now data and instruction are actually merged together in the same thing. So we mix them up. And what we have to do is we have to filter out the data to try and identify the instruction. And we use bit masking to determine that. So my opcode, I guess, is just a hash table of all the opcodes in their hexadecimal representation. But as you can see, CLS is clear screen if you were going to write it in assembly, but it would actually be output as 00E0 in binary or hexadecimal. But yeah, okay. So let's see if let's do the pattern matching ourselves, so I can show you how that works. So when we do a bitwise AND operation on our opcode and F0FF, we end up with this. So this is basically how you do an AND operation. Okay, is the way an AND operation works is both sides have to be set for them to remain in the output. So A and F are set, so we end up with A. 2 and 0, well, 2 is set, well, it's greater than 0, but 0 is not, so obviously, so that stays as 0. And then F, B and F, obviously B, and then 4 and F, well, we end up with 4. So that's basically our first attempt at stripping out the data. And then what we do is we check that against our list of opcodes, and we see if we can find a match. So it was A0B4. Well, there's an A, but no A0B4. So we try again with a more strict, I guess, matching pattern. So it's now F00F, which is A004. But guess what? There isn't any in the tree, so it won't find anything at that point. And then we end up with A000, which we look through the tree and we find our opcode. So there we go. We've done our decoding, and now we have our operation. And basically, what this operation does, is it does a bitwise AND operation again. And if we were to, after doing this a couple of times, you can just see this automatically. But that's going to store the value 2B4 into the incrementer, or the I register. And that's basically it. We just did our first instruction in assembly, and that's what the processor would have done. And let's say it couldn't find an opcode, or we done all our pattern matching and we couldn't find it. It would just throw an error and help me debug it by console logging out some information. But yeah, basically it runs the instruction and then it increments the program counter. Well, it actually does that first, but So it moves to the next position in memory to prepare for reading the next instruction. And then we handle our timers. So basically, if sound is greater than 0, it'll beep. And I'll explain what this is doing in a second. And yeah, we don't want our timers to decrement on every cycle, but so we have it doing it every second cycle. And then we repeat the process. So that's basically our whole processor. There's like nothing too crazy there. You know, it might seem really complicated, but it's actually really simple. And what our program will do is, okay, yeah, and basically our processor is going to read A2B4. It's going to load something into the registry, and then it's going to do the next instruction, which is 23E6. So let's just do that really quickly. 23E6. E6. I know for a fact there's no instruction. If we were to bit mask that, there's no 2E6 instruction. And if we were to bit mask that again, is there a 2006 instruction? No, there's a 2000 instruction, so let's look at what that does. It will, okay, so this is going to do a jump command. So if you're writing assembly, you would write JP and then the address that you would write, and it would turn it into what we saw. So it's going to do a jump to the 3E6 memory address. So if you have a look, it'll add that. It'll store our current position in the current program that we're executing at the moment, the current position in memory, into the stack, and then it will set the program counter to that position in memory, and then it will probably change where it's executing, and it will return to it once it gets another instruction saying return to your previous instruction. So that's basically our processor and how processing works. And yeah, so it's really simple. And yeah, so now I'm going to show you guys how drawing works and how we draw to the screen, and this is where I show you how to communicate with the terminal. It's really simple. We just loop over our screen, or we loop over every line in our screen, and then we loop over every pixel in that line, and then we check if the current screen, our current screen in memory has had anything changed, or that position has changed, and if it hasn't, we just let it go. But if it has changed, then we render we make an actual change on the screen. So we try and minimize the amount of drawing that we do. And it looks a bit funny. You know, it's like, what's going on here? What's all this craziness? And this is where I tell you how the drawing actually works, or how to draw with the terminal. So the first thing is TTY. Does anyone know what TTY stands for or means? Yeah, teletype. So back in the day in computing land, we didn't have monitors. We had these things that would just print out reams and reams of paper. Yeah, and basically that's how we got output from our computers. Fast forward to 2013, and we still use TTYs. So this terminal that we ran this game in, it's actually an emulated TTY. So it works the exact same way. And what happened is, originally, TTYs, they ran in this mode called canonical mode, which basically meant that, I'll show you this. So when you type and you get to the end of the line, it shouldn't go to another screen. That's bad. But when you type, when you get to the end of the line, it will automatically do a carriage return for you and make things pretty. And that was to save on the amount of communication that happened along the wire. But then things got more advanced, and we got like actual monitors. So Steve Jobs made his little Apple thing and gave us monitors, and we communicated to mainframes at banks and stuff. You can see in all those really old 80s movies. But yeah, so people started to get the need to actually draw to the terminal, and we needed to actually control the cursor. So you got this mode called raw mode, which means you don't get any of that auto help. It doesn't control the position of the cursor for you, and you have to do it yourself. And that's basically what we set our terminal into. So if you have a look, you'll see that I set raw mode to true. And that's basically how easy it is with Node. Node's awesome. And then what we do is we send a series of instructions to control where the cursor is, what color the foreground is going to be, and what color the background is going to be. And we just print characters to the screen. And that's basically how we do our drawing. So if you have a look here, this first line, basically, we start off with an empty string. So we're preparing to send an instruction to the computer, to the terminal, which is nothing at the moment. And the first thing is move yourself. Oh, shit. First line is move your cursor to whatever coordinate we're currently looking at. And then basically this command here actually changes the color of the background. Because I use, if you look at our thing, you'll see that I just used the green background to denote a pixel being on. Yeah, so, and basically if the pixel has been set, then I change it to green, which is what 42 is. But if it hasn't, then I set it to 40. And I do that for every pixel, or every pixel that's changed. And then all I do is I write that buffer. I just write that into the stream, and the terminal picks it up and processes it one by one. So there's a really cool library that I see everybody using called colorize.js or something. It's an NPM library. Colors.js, that's right. Yeah. So if you're just going to change one thing's color, you probably don't need to use that library. You can just do this yourself and just echo this out and make sure you reset the colors once you're done, or everything will end up being blue or green or whatever crazy color you use. And that's basically how you communicate with the terminal. So you can move the cursor and you can change colors, and that's how we do our crazy drawing. Now, I don't draw every single time the CPU cycles. It's actually in a different loop itself. And I draw every 60 milliseconds, or approximately every 60 milliseconds. So, yeah, so it doesn't slow down, because terminals, this is something to keep in mind when you're programming to terminal, is your actual execution will stop until the terminal responds. And that's because back in the day, your terminal itself was really slow, because it actually had to move a mechanical arm to a certain point to print. And if you were sending too many commands to it, its buffer would overflow, and then it would forget what to print, and you just end up with garbage. So the actual system means that you can't send the next command, or maybe there's a pool of commands that you can't send until the buffer, until that action has been completed. So that's why when you communicate with the terminal, you don't want it to hold up execution. So good thing that Node's async. You didn't have to worry about creating new threads or anything like that. It basically just did another tick, as you can see down here. So they're my two loops. And yeah, so that's basically how processes work and how I wrote my chip 8. And if I haven't, if I've inspired someone to create their own processor, or go off and go into emulating, it's really fun. There was 35 opcodes there, and I felt like every time I implemented an opcode, I just passed another level in the game. It starts off really easy, and then you get to really hard ones, and then you just skip them. Then you come back to them a week later, and you still can't figure them out. So you go and check out Alex's source code. You're like, that's how it's done. Then you just copy him. And then you come back a week later, and you're like, oh, I can't believe, and you just do it yourself. So if I've inspired you guys to create your own emulator project, you'll learn a lot about how the low-level operations of systems work, or processes work, and they won't just seem like magic to you anymore. This is some advice I can give you. Start with chip 8. It's really easy. I did it in like 220 lines, so you won't spend months on it, and that will really set you up to writing your own. Okay, once you've done that, you want to choose an emulator or a system you want to emulate. Make sure that system is well documented if it's your second attempt or your second project, because if you can't find information about a system, there's no way you're going to be emulating it. And I mean like proper technical spec on how each instruction works, what the components are, how they work. So that's the next thing. So doing something like Nintendo, the 6502 processor, which is what runs Bender in Futurama. The same thing that runs the NES, the Commodore 64, and the Apple Lisa 2. It's a bigger step up. It's a much bigger step up than Chip 8, but Chip 8 will give you, I guess, the confidence needed to take on that project. And that is well documented. Try and get your hands on a test suite if you can, which is basically a piece of software written to test emulators, and that'll tell you where you're going wrong or what's not done properly and things like that. Get really good at Googling. That's always going to save you. You might get in touch with people that have written emulators before, and they might help you out. And get really good at walking through assembly, because you have to do that when you're trying to figure out why things aren't going right in your code. So actually doing what we just did before and looking at each line and seeing if the program executes the same way. You need a lot of time, obviously. You know, these hobby projects do consume you. So it's a good thing not to give up on them. And the way I found, I guess, what speeded up my development and actually debugging all my opcodes and things like that was comparing the output from one emulator to another. So what I did is I got Alex's emulator, and I rewired it. I got it running in Node, which is really, really easy. It's like 10 lines change. And I got it to print out its opcode list, which is basically why we had that buffer flag in my code. So let's exit this. And Q. No, L. So yeah, basically I print out this list, which is each instruction and the register states, and then I do the exact same thing with Alex's, and I'd compare them, and where they diverged is where my emulator was broken, and I'd fix it to the point where it diverged. But if you do that, you need to worry about some things. You need to make sure the timing is exactly the same. So your timers work the same way, or your programs will diverge at different times, and you just think yours is wrong when it isn't. As well as you have to take all randomness out of the system and the other system as well, because if there's a random number, it'll mean that instructions happen differently, and then your things will diverge automatically. So what you do is you find the instruction where, like I said, processors are really dumb. There's only like one way to get a random number here. And this is it, this instruction, the random R&D instruction. And you just change this to a static number like 5. And then, voila, both systems work the exact same way. I'm not bothered full screen this, sorry. And that's it. So, thanks. Oh, any questions? Sorry.
What sort of ROMs can you get for Chip 8?
I'll show you a list. Sorry? Yeah, there's not many. They're all written in like the 70s and 80s and stuff. But
did you try writing your own ROMs? Is that like another thing entirely?
Yeah, that's actually another thing. But doing the emulator will give you a very it'll position you well to doing that as well. But yeah, no, there's actually there's actually guides to writing Chip 8 ROMs as well. But yeah, that's just to show you the games. I think I've got a pretty good pack here. Chip 8. Alright, I'm just going to do this. Early games. So, yeah, there's like, I don't know, Single Dragon, Soccer Baron. I've never heard of it. Where are these crappy games coming from?
It's like that with us.
Okay. Yeah, sorry. I apologize. Yeah. So there's like Space Invaders, there's Breakout, and things like that.
Keep up this.
Yeah, and there's some test suites. But it's really fun, and you can get a lot of life out of Chip 8 as well, because there's modified versions, like there's Super Chip 8, which has more instructions, and then there's another version which has a higher resolution screen, and so yeah, you can end up playing some pretty crazy games on it. I just like Tetris because it's fun.
Have you seen 228's ANSI module?
Maybe.
Okay. I'm not sure like how much it would help for emulating, but it's really easy to move the cursor around the terminal and like pick up the window size and stuff like that. If you look into it.
Or you can just throw it on canvas.
Yeah.
Yeah.
I wanted to do something different.
Why not write it for the browser? For
You put canvas in the terminal, like with ANSI characters.
Yeah. Is that the Git repo where they show Zelda A Link to the Past, and he's like, don't try. This is actually. He's like, it's fake.
This is Photoshop.
Yeah. I've seen that repo. I was like, whoa, it's amazing, and it's like fake. Not using the
It's
repo.
got an okay like animated problem.
Well, yeah, I guess you could do that. It'd save you a bit of time. Yeah. Any other questions?
It's more of a, I guess, history question than anything else.
Yeah.
But do you know why data and code are matched together and you have to extract one from the other? Was it just a memory constraint, or
Just put more data into less memory size.
then your code not be just half as long? And
Well,
Compression.
yeah, it's really efficient, and processors basically were implemented in hardware. So I think I've got in my slide.
And all these transistors you can actually do it manually and
This is actually a bad example, but this is like
of course it is quick.
yeah. So that's sort of why, like, they had to, the way the circuitry was designed and things like that were, it was an early implementation. So it actually gets a lot crazier when you look at like more advanced processors. You got multiple addressing modes, so the length of the instruction can change. And yeah, but I think the primary reason is the way the hardware is actually wired up.
Looks like chip 8 has traded off. Instead of using an 8-bit instruction set, which all of the old 8-bit processors used, they've gone to a 16-bit instruction, and that way they can move to RISC and just encode everything in just one fixed instruction size. Okay. Simplify the decoding a lot. You can see in this code it's only.
you obviously have some hardware constraints.
Chip 8 is really simple because it never really existed in hardware, and that's why it's a good starting point. But when you implement something like the 6502, it actually has a lot of complexity in emulating because of the trade-offs made in hardware. So
We can probably transform this application to something like event-based, state-based.
yeah, I mean that's a lot of fun.
As an example, like, as a further improvement.
Yeah, getting it running on the server and pushing the stuff to the. It wouldn't be very efficient because if you see how many times this thing actually draws the screen, it's crazy. But yeah, there's always a lot of stuff you can do to improve and optimize your emulator, and that's always a fun game as well.
As a cool aside, in 6502 it had about 158 instructions, and the decoding was just fairly lackadaisical, just enough to get those instructions decoded. So what people would do was actually use some of the other 100-odd codes and use those, and they would often decode to 2 instructions at the same time, so you'd get load from address, comma x, plus increment y. And so they'd get 2 instructions for 1 in the same thing. That's great for doing ridiculous.
So a lot of ways to optimize it actually, so you can squeeze your huge game into some really small size because of that.
Yeah, well, when you look at these ROMs and you actually start processing the assembly yourself, you see how advanced, or what kind of advanced things you could get out of such little amount of binary. It's amazing. It makes you kind of feel a bit weak with your, 20,000 line JavaScript thing that does something.
Just to validate email.
Yeah, no, it's pretty cool, and I'm guessing this stuff is less relevant as we go on in time, so it's a good thing to try and keep a hold of it.
It's the opcode decoding bitmaps. It's very interesting. Do you have any idea why did they decode it in that way? Like first byte, then first.
Because they all seem to be A and then 3, whatever.
Yeah, like why didn't they just say, okay, either the first or the first and second of the 4 bytes are the instruction, like bitmask those two? Why is it first, then first, third, fourth, then first and fourth? What's the go there? Any idea?
Alright, so it's because of the X and Y, and the X and Y point is always going to be, so basically X and Y point to register numbers. So this might be register 5 and register 6, and then it does an OR operation. It stores the result back into register 5, and that's how it'll do things like add together. And the reason, what they did is X and Y is always the first, the second and the third. So if the second and third are going to be used as X, Y, then the last instruction that's the only thing that's left to add as instruction.
Why not the last two? It just seems a really weird way of coding. There must be some.
The last two. The reason is because sometimes you use X, but you don't use Y. Let me find it. Yeah. So here. So I think that, like when we look at here, we use X. So F. It could be F6. F615 would store whatever's in register. It'll set the delay timer to whatever in register 6. But it's still a valid point. I mean, I don't know. I mean, you could have done it the other way, but
maybe there's some odd design decision.
Yeah, the guy was like,
it seems arbitrary, but I guess a lot of this comes across as quite arbitrary that it's been going through.
Yeah. Well, the chip eight's pretty sane when you look at 6502 and stuff. It's yeah, I don't know. I scratched my head a couple of times. So. Yeah.
I have one last question. I was just hoping someone could confirm. You mentioned that the TTY is blocking for, I guess, historical reasons. Is console log still blocking in Node?
Yes.
Does it mean if you leave one in your production system, it will block your event loop?
Don't leave one in your production system.
Okay. Always had a doubt about that. Yeah.
Sorry, no console that logs in your production system.
Yeah.
Is that what we're saying?
Yes.
No.
Yeah. You can actually get some, like, I think in some of the places I've worked, they actually have like a grunt task that will remove all console.logs.
Wow.
So just in case someone forgets them.
So how do you log?
Use database.
You can use a logging library. I think one.
Stream or
Winston?
Winston's
Yeah. I don't log anything, so I don't really have much to say on that front.
Just a little note there.
You can actually, if you don't want to library, log things to database because it's synchronous. Ready, so
Good question.
LairDB.
LevelDB. Or CouchDB. Yeah, so any other questions? So I didn't put anyone to sleep.
That was cool. Assembly, something. That's great.
Thanks a lot.
Thanks. I have a question, not about this, but about LevelDB. Just a simple question is.